Alright, good morning, and here we are for yet another lovely day of CENG 306 Mechanics and Materials. I hope you all enjoyed your weekend. It's now over, if it ever began. Here we are again. So, bit of business for the students watching this video this semester. This is our last week of Mechanics and Materials. We will have lectures Monday through Thursday, and then we'll have the final exam on Friday. Again, for students watching it this semester. If any of you are watching this in later semesters, you're on your own. Unless I'm your instructor, then I guess you're not so on your own, but for this you are, maybe. Whatever. Okay, let's actually get to the topic at hand. Okay, so that was a bit rambling, that's okay. So today we are going to start with what I would call lesson 33, which is really the derivation of the formula for deflection and curvature of elastic beams. So everything we have worked with previously, in static, let me back up. In statics, you learned how to calculate shear and bending moment at any point along a beam, given an arbitrary loading. And we reviewed that a bit in this course. And then we extended that to go and find the stresses and to find the stresses within beams under various kinds of loading. And now we are going to find the actual deformation. So you know how to find the stress in, say, pounds per square inch, kips per square inch, megapascals, etc. in a beam at any location along that beam from either shear or moment, but you do not yet know exactly how to find the actual deformation. What I mean by that is, if I have a beam that's, say, 20 feet long and I apply a 10 kip load in the middle of it, how far is it going to actually bend? Literally, if I had a very precise ruler and measured it, how many inches or fractions of an inch would it bend? And so that is what we want to derive today. So in the first part of the lecture, I want to derive the formula for elastic curvature and deflection, and then in the second part, we are going to work on sort of applying those relationships. So let me look at, I'll call this deflection by integration. So we're going to use some differential equations today. Isn't that lovely? Deflection by integration. Deflection by integration. And then we're going to look within this at, so that's our goal. We want to be able to calculate this. And we are going to look at the geometry of elastic curves. Now, consider an element. I'm going to base this analysis of the following diagram. So here, I'm going to have a d theta, or in other words, well, let me just draw it and then I'll explain it. It might make a little more sense if I draw it rather than just trying to explain it directly. Here. So we're going to look at a differential element of a beam. And the actual beam is here. That looks really bad. It's slightly less bad. And in purple, I'm going to draw the neutral axis here. And this beam is going to, actually, I think I'm going to modify this. I'm going to make the actual beam, I'm going to save the black for just the beam. And then maybe make this in green or something like that to show that these are dimensions. Where these meet up will be more like that. So perfectly circular arcs, perfectly straight lines, just like I always draw. Okay, so I have this beam, and it started out horizontal. I have this actually this is a small dx of a beam, but it is under a bending moment m. This is a small enough element that we can consider the moment on the left the same as the moment on the right. And I have at the center the neutral axis, or actually it wouldn't necessarily have to be at the center. but I'm just sort of drawing it there. Neutral axis. Now, this beam started out perfectly horizontal, and there we would have a dx if we considered a distance x along the beam. However, at the neutral axis, something special happens. Dx is equal to ds. In other words, the change in the length of this differential element is the same as the arc length here. If we have anything not at the neutral axis, say right up here, the dx will be greater than ds. Here, dx would be less than ds. But right here at the neutral axis, the actual length of the beam is equal to the arc length. And along with a dx and a ds, I'm going to need a d theta. D theta is the angle, is the little differential element of angle. If this is a perfectly horizontal beam, the theta would be infinite, wouldn't it? Or yeah, the theta would be infinity, wouldn't it? Yeah, or actually no, sorry, the theta would be 180 degrees. Theta would be 180 degrees if that were the case, if this were a perfectly horizontal beam. But because it's not, we end up with a d theta that is not 180. It's a finite number. It's a number less than 180 degrees. Now, some other things that we'll need to consider here. I'm going to have coordinates y, which is the same thing we've always had, which is measured upward from the neutral axis. And then I'm going to have what I call rho, which we saw earlier when we were dealing with torsion, has something to do with radius, and it will. Rho here is going to be our 0 point here. Rho is the radius of curvature. And then finally, here, I can maybe label this as ds prime. ds prime would be the arc length at the outermost fiber. Okay, and then some other notes here. And we do need to keep in mind, recall, at the neutral axis, the stress and strain due to bending is 0. So in this slide, all I'm doing is just defining a few key terms. Next, I want to relate this to strain. So let's consider normal strain on any fiber. Normal strain on any fiber. If I were teaching this class in England, we could do FIBRE, but we're in America and we have good, strong American steel, so we do FIBER. Okay, but that has nothing to do with mechanics of materials. Really bad jokes this morning. So we're going to have a so I'm just going to make my familiar strain diagram for a linearly elastic material under elastic bending. You've seen this a million times by now, you're probably getting sick of it, but it's good to remind us what this is. So we're going to have this here. Up here I'm going to have negative strain at the upper zone because it's going to be in compression. And the lower fibers are going to be in tension. So I'm going to have a strain like this. Here, strain will be positive. Now, in terms of the other relationship, or another relationship, strain is going to be equal to, let's see, actually ds prime probably should define it as the initial, or the, sorry, that's fine. Strain is if you just construct a relationship of similar triangles, you can find that strain is going to be equal to ds prime minus ds over ds. ds prime minus ds over ds. But we have a few other things. We also know that ds equals rho d theta, and that ds prime equals rho plus negative y times d theta. And then that can give you, if you work through it, strain, if we substitute this in, strain is equal to rho plus negative y d theta minus rho d theta divided by rho d theta. And the d thetas will all cancel out. And this will give us that strain is equal to negative y over rho. Strain is equal to negative y over rho. So that can be useful. So basically what we're doing is we're just going through and gathering a series of tools that I promise will eventually result in something we can actually use. So next, in my random assortment of mathematical treasures, I'm going to pick up Hooke's law. Hooke's law. And we remember from previous material and from previous courses, maybe even just elementary physics, that Hooke's law states that stress is equal to strain times the modulus of elasticity. Sigma equals epsilon times capital E. But if I interpret this as a function, what I can say is sigma as a function of y equals E times epsilon of y. So E times epsilon of y. So let me express this. Let me note that again. What these are. This is stress as a function of beam depth. Something weird with my pad. Something with the writing pad makes it want to jump up like that. Interesting. Stress as a function of beam depth. Of beam depth. And epsilon of y, this is strain as a function of beam depth. A function of beam depth. Okay. Now, if I look at the moment equilibrium about the neutral axis, so let's next look at moment equilibrium. Colors don't match. That's important for some reason. Uh-oh. Well. Moment equilibrium, or equilibrium if you prefer. Moment equilibrium about the neutral axis. So I want to look at the moment relationship of these stresses here. So then if I have the maybe neutral axis in purple down here, and I draw a stress diagram, well, I'll have the following stress distribution. Again, this is the same one as before. Same exact stress distribution as before, except we're going to look at the kind of moment it creates. So this is our maximum sigma in compression, and this down here is our maximum sigma in tension. And then, let's see, all of this will come together to form a moment, form a certain bending moment, and we measure y, again, from the neutral axis. So, and we have a little, at any given point, our stress is applied to a dA. And the relationship here, then, is that the moment m is equal to negative the area integral of sigma of y dA times y, where, if I annotate this, this is going to be the force, and times the distance from the neutral axis. So we're getting closer. Oh, and again, this is the, if I annotate this, this is the sigma of y. Stress as a, normal stress is a function of y distribution. Okay. So next I will again apply Hooke's law, or I'll actually, I listed it before, but now I actually wish to apply it. So apply Hooke's law. Not to be confused with Captain Hooke's law, which is something different entirely. Strain as a function of y is equal to negative y over rho. I wonder if there's ever been someone in the Navy with a last name Hooke, and if they ever got crap for that. There probably has been, but anyway, that has nothing to do with mechanics of materials. Really bad jokes. Okay, so if I apply, basically if I just combine this, oh wait, yeah, so we have this here that we got back here, and if we combine that with the Hooke's law, we can get that m equals, okay, so here, the negative integral, area integral of E times epsilon of y times y dA. Basically just combining this stuff together. And this is equal to the area integral times E of y squared over rho dA. And we get this from the knowledge that dx is equal to rho d theta, or this leads us to, actually, sorry, this isn't developed from this, this is what we're going to use for the next step, and this leads us to rho equals dx over d theta, or simply 1 over rho equals d theta over dx. So we have this relationship here that we got. Basically, we've combined this with our previous, we've combined this with this with this to get this relationship here. And then, finally, we can say that m is equal to the area integral of E times y squared d theta over dx dA. Now, I know this is an area integral, so I can do something kind of neat here. I'm going to pull this and this out. Pull these out because this is an area integral. They do not, both of these are constant across area. Are constant across the area. They vary across the length of the beam. Well, this doesn't. This is actually a material property. D theta dx will vary across the beam, the length of the beam, but it will not vary across a cross section. Are constant across area. And we can actually then say the m is equal to e d theta dx of the integral of y squared dA. Area integral here. However, I've seen this before. I took statics. Y'all took statics. You know what this is. This is the moment of inertia. So in other words, m is equal to ei times d theta over dx. D theta over dx. And this then is also equal to, and that's a little messy, let me fix that. M is ei times d theta over dx, and again, we're not quite where we want to be finally. But we're getting there, we're getting closer to something useful. And this is 1 over rho. So we're almost to something useful. And then I can use the relationship that, among some of these variables, that d theta over dx is equal to m over ei. And this equals 1 over rho. And what is 1 over rho, though? What actually is 1 over rho? 1 over rho is something special. It is the curvature at a point. In other words, simply 1 over p is 1 over rho is defined as the curvature. That is the definition of curvature. It is 1 divided by the radius. So if we then separate the variables, so if I then separate some variables, we separate the variables, we will get the relationship that d theta equals m over ei dx, or if I apply some basic calculus, I integrate both sides, I will get the theta as a function of x is equal to the integral of m as a function of x over ei dx. And this is something really useful. I'm going to put a big red box in it just because it's that important. So this is one of our final desired results. This is the slope at a point x. At a point x, or mainly slope as a function of x. This is the slope on a beam as a function of x. So we've actually got something useful now. Very good. But we're not done yet. I promised you the formula for deflection. I'm going to give you the formula for deflection. Deflection or bust here. So let us relate deflection to curvature. Okay. Now, I have this relationship that you can find in a calculus textbook. 1 over rho, or 1 over radius, can be 1 over rho is equal to d squared y over dx squared over, this basically just comes from a calculus textbook, 1 plus dy over dx squared, and all of this to a lovely 3/2 power. Isn't that nice? Okay. Now, we are going to make an assumption here. just like we always make assumptions in engineering, just like we make the assumption that, say, something is linearly elastic or that we have a constant cross-section, etc., I am going to make what is known as a small deflection or a small angle assumption. So I'm going to assume this is 0 via a small deflection assumption. This is very similar, if you remember, say, when you took chemistry way back in the day. Do you remember when you took chemistry way back in the day and you had to do those like Rice tables or something like that, where you had, you would assume that the change in X, say like an acid-base equilibrium or something like that, was small, and because it was in the denominator, things or something like that. The general rule is, as long as your changes are small, if you are multiplying or dividing by a small number, it will dramatically change the result. If I have 10 and I divide or multiply by 0.1, it will change the result significantly. Let me actually I'll say 0.001 or something. If I have, say, 50 and I multiply or divide by 0.001, it's going to change the result substantially. However, simply adding or subtracting by a very small number is not going to change our results significantly. If I have 50 and I add or subtract 0.001, it does not change the result substantially. So I am going to assume that this is 0. So what we're left with is 1 to the 3/2 power, and 1 to the 3/2 power is simply just 1. This is a very common assumption in structural analysis, the small angle assumption, the small deformation assumption, and really this is a perfectly valid assumption, because if we do not have a small deformation, in other words, if our deflection is of similar magnitude to our beam, what we're saying when we're saying a small deformation, what we really mean is in relation to the length of the beam. If our beam is 10 feet long or 20 foot long, and our deflection is usually only a fraction of an inch, or even a max an inch or two, even for a visible deflection, it's only an inch or two. But if you have a beam that is 10 feet long and your deflection is a foot, your beam has basically already failed. As long as you are going to be well outside the elastic range, you probably past the point of rupture. So if you, as long as we're using the elastic assumption, this is going to be a perfectly valid assumption. If we're doing something really screwy, like purposely loading beams beyond the point of rupture or something really insane like that, well then maybe we'll have to use a higher order analysis, but for this will suffice. Okay, 1 over rho is going to be the second derivative, d squared y over dx squared, and then m over ei, getting this from previous, is simply, so plug that into m over ei, 1 over rho. M over ei is equal to the same second derivative, d squared y over dx squared, and then the integral of m as a function of x over ei. So I'm going to basically distribute the dx, and then, I'll keep in mind, let me back up. I want to keep in mind that the previous formula, the integral of m over x, m of x over ei is equal to dy over dx is equal to theta of x. I'm going to use that. And finally, combining it all together, the double integral of m as a function of x over ei dx, the double integral for x, is equal to the integral of theta of x dx or y of x. So, in other words, the actual deflection in a beam at a point x is simply equal to the double integral of m, of the moment function, or the single integral of the curvature. Of the curvature. Or sorry, it's not the curvature, of the slope. 1 over rho is curvature, theta is slope. We've got to be very careful with our language here. So this is also one of our big formulas. And what this is, again, is the deflection at point x as a function of x. Very useful. And again, let us look at all of our assumptions. So assumptions built into this. Well, the assumptions that we're going to use are 1, straight beams, 2, transverse loads. So we're assuming the load is applied as a, say, a downward load or an upward load or anything like that. Transverse loads. We're assuming Hooke's law is applicable. You may have some exotic situations where that is not the case, but for normal friendly materials that's going to work as long as you're not loading it past the elastic range. Hooke's law, plane sections, and also small angles / deflections. As long as you keep these assumptions true, these equations will work out. So finally, let me go and summarize all this. I want to create a great big table of all of the equations that we've seen so far for beams. Well, maybe leaving out yeah, most of them. Not the stresses, but the actual quantities. So summary. W of x is our load function. W of x is simply defined as our load function. And then I'm going to have 4 quantities. We now have the complete set. We have shear, which is V as a function of x. We have moment, which is M as a function of x. We have slope, which is theta of x. And we have deflection, which is equal to y of x. And these are then equal to, we have this integral relationship, equal to the integral of negative w of x dx. This is equal to the integral of v of x dx. This is equal to the integral of m of x over ei dx. And this is equal to the double integral of m over x over ei dx, or also equal to the integral of theta of x dx. Now, it is something interesting to note about this. Notice the shear and moment we don't need to know anything about the beam itself. We do not know anything about the material it's made of. We don't know anything about the cross-sectional area, the moment of inertia, anything like that. We know nothing about the beam itself other than its length to develop the shear and the moment. But to actually develop the curvature and to actually develop the slope and therefore the curvature and the deflection, you are going to need to know something about the beam. You're going to need to know the cross-section, and you're going to need to know what it's made of. So here, this is statics alone. This you need mechanics of materials. And then finally, I will list these equations have slightly different form on the FE equation packet. What you'll get on the FE exam, you might see a slightly different form. Load function. So let me do the load function. The shear, this one is maybe expressed as a derivative relationship sometime. Slope, again, theta of x, and deflection, y of x. Y of x, and what these are equal to then is, they use q of x for the load function. Q of x equals negative dv of x over dx, negative dv of x dx. They say v of x is equal to d m of x over dx. The slope, they use the same kind of thing that we did. EI dy over dx, which is the slope, or theta of x, equals the integral of m as a function of x dx. And they say the deflection y of x, I'm going to just squeeze this over here. EI y of x equals the double integral of m as a function of x dx dx. Double integral with respect to x. Alright, and that will do it. That is the full and complete derivation for the slope and deflection equation. So, the next part of the lecture we will look at actually applying this, and that is what we will continue on after the break. Alright, that'll do it, and thank you.